let's see how does the forwarding happens, which means suppose some packet is coming to this router R1, and then how does this router determine to which path it should route to. So suppose like there is some packet which is coming. Okay, I'm taking one packet that is intended to go to this network. So can you give me any example that belongs to this network, some IP address that belongs to this network. This network is saying that you should be having 180.170.65 dot this is one, and then you can take anything here. So let's take one example which is 11 and then all zeros, which is 192. So I'm taking one of the example from this network, one of the host from this network. This is 180.70.65.192. So suppose that there is some packet that is coming to R1 with this destination IP. So this is the destination IP address that is the packet is having, and that packet is coming to this router R1. Now R1 has to determine that R1 should route this packet to which interface, either to M0 or to M1, to M2 or to M3. So how R1 is going to determine, that's what we need to study in this lecture, and then we will be studying some of the optimizations in that. Now one thing is that there are few fields that are required for the R1 or any router to have in any routing table. So one of the field is called network ID, that is NID, for each network to which it is connected to. So it is connected to these four networks, and these are the four network IDs that I have. And another thing is that network mask or the prefix length. So this 25, 22, 26, 24, these are called mask length or the prefix length. So another field is prefix length. Prefix length. And third field is interface. These are the three fields which are must for any router. It says that if the network ID is this and prefix length is this, then interface should be M0. If the network ID is this 201.4.16.0 and prefix length is 22, then interface should be M1. Like that, it should be having all the network IDs and corresponding prefix length and corresponding interface. This is what we call routing table. This is how routing table looks like. Now the question is still open, that how this router is going to determine that to which packet it should route this packet, right, which is having this destination IP. Now this is very simple. What we are going to do, we are going to take this destination IP, and then we are going to check this destination IP belongs to which network. How we are going to check it? What we are going to do, we are going to apply this mask, which means we are just going to say, okay, let me find out if this is the destination IP. Then if I apply 25 here, then let me find out the network ID, corresponding network ID, which means if I just fix initial 25 bits fix and just make all the remaining bits to be 0, all the host IDs to be 0, then I will be getting the network ID, right? Then you will be saying that initial 25 bits are this 65.1, and then this is basically 1 and then all zeros, but initial 25 bits are just this. Then they are saying that just fix that and convert everything to zeros. Then what will the corresponding network ID? It is 180.70.65.128. Now is this network ID matching with my network ID that I have in the corresponding column? Yes, it is matching. This is also 128. Then it needs to route this packet to interface M0. And that is in fact true. Like this IP address, this host address belongs to this network, right? This is one of the hosts from this network. So what it does, it basically checks that how, like it basically checks that in which network this packet belongs to, and how it is going to check, using this prefix length. So what it is going to do, it is going to apply the prefix on this destination IP. So destination IP is given to us, and then the prefix will be taken from the routing table. Prefix will be taken from the routing table, which is /25, and then from these two it is going to find network ID. Is this network ID matches this network ID? If yes, then it will forward to M0. So again, see here what we are doing. We are having few fields here, right? One is network ID, another one is prefix length, another one is interface. Now if some packet is coming, let's suppose this is some network ID which is let's suppose ABCD, prefix length is let's suppose N1, N2, N3, N4, and interface is let's suppose M0, M1, M2, M3. Okay, now what it is going to do, if some packet is coming with some IP address, let's suppose this is the IP address which is IP1. This is the IP address of the packet which is having this IP address is a destination IP address. Then what we are going to do, we are going to take this IP address and then this prefix length which is N1 IP1, and then we are going to apply this N1 to this IP address. Then we are going to find out some network ID, right? Some network ID. Is this network ID matching? Is this equal to A? If yes, yes, then forward to M0. If no, no, then check next prefix, right? This is how we are going to do. So what we are going to do, we are going to say that if this network ID, whatever is the network ID here, see in this example, if this network ID is matching to the network ID after applying the prefix, which is logical in fact. If this IP address belongs to this network, then this IP address has to have the same network ID, right? So that is why it makes sense. So that's how the forwarding of IP packet happens. I hope you got the idea. So suppose let's take one more packet. Suppose there is some packet from this another network. Let me copy this. Let me go to the next page. Suppose there is some packet that belongs to another network, which is, suppose in this case this is 201.4.22.0. From this network there is some packet that belongs to this network. So can you give me some IP address that belongs to this network? Maybe this initial 24 bits are fixed, so this is okay. Then let me take anything, maybe it 128, right? Because initial 20 after initial 24 bits anything is host ID, so I'm just taking 128. Now suppose this is the destination IP address. Now what do you think, if any packet with this destination IP address comes to this router, then to which interface it should route to? It should route to M3, because it in fact belongs to this network, right? So if some packet is coming with this IP address, if some packet is coming from this IP address to R1, then it should route to M3. That is very logical. How it is going to do? It is just going to apply this mask of 24 mask. Then it is going to find out the network ID, which is just this. Is this network ID matching to the network ID of the routing table? So in the routing table, we must be having network ID, which is this, corresponding mask, which is 24, corresponding interface M3, right? Is this network ID matching to this network ID? If yes, then it will forward to M3, which is also logical. I hope you got the idea. Now let's go to the next page. So here I have the routing table, but what I did here, I have just combined the network ID or network address and mask together. So instead of writing in two columns, I'm just writing in one column. I hope that is okay to everyone. Now let's see this. In this scenario, what I have two routers, R1 and R2. R1 is connected to 4 networks which are like this. R2 is connected to R1 which is like this. So for R2 there are two interfaces, M0 and M1. For R1 there are 4 interfaces, in fact 5 interfaces, M0, M1, M2, M3 and M4. Now suppose some packet is coming to R1, like from any of the interface, from either M1, either M4, any of the interface. So I'm not writing the interface name. Suppose some packet is coming to R1. Then R1 has to decide to which interface it should go to, right? Similarly, that is the case for R2. If some packet is coming to R2, suppose from M1, then R2 has to decide to which interface it should go to. I mean, either M0 or it should go to M1. If that is coming from M1, that it is very unlikely that it will go back to M1. But if that is coming from M0, then only it may go to M1. If some packet is coming from M1, then it is very likely to go to M0. Now let me do one thing. Let me write the routing table for R1 and R2 both. So what will be the routing table for R1? Can you try it? Routing table for R1. There are, let me just give you a hint. There are three fields. One is network ID, another one is mask or the prefix length, another one is interface. So that is very easy actually. What you can do, you can just copy this. This is the network ID. This is mask. This is interface. This is network ID. Similarly, 140.24.7.64, and this is mask. This is interface. Like that, you can fill out the entries for R1. I think I have that in the next page. Yes, I have that in the next page. So these are the entries for R1. You can do what? You can just fill the network ID and the mask and then interface. Very easy. And last entry, just default entry, which says if none of the entry matches, then go to the M4. That's what it is saying. That is okay. I hope you got how we are making the routing table. Now, what about R2? How R2 routing table will look like? Just think about it. See, R2 is also indirectly connected to these four networks. So there is no problem if I just write the R2 routing table almost as it is, which means, so let me just copy this and let me just show you that how I'm going to write the routing table for R2 or forwarding table or routing table. So I don't know where to put it. Maybe let me put this in the next page. This is the routing table for, let's suppose, R2, not R1, and let me just try to modify it a little bit. So there will be only two interfaces, M0 and M1. This is R2. Let me also copy this. Now for R2, I can say that if that is the network, if any of this network, then it will go to M0 obviously. If any of this network, then it will go to M0 only. M0, M0, M0. Otherwise it may go to M1, or if that is something, some network is connected to M1, then I can say M1, or otherwise I can say by default it should go to M1, because if none of this network if the packet is not intended to go to one of this network, then it should go to M1. So by default I can say M1. Now you can see one thing, that there is some redundancy, which means it is saying M0, 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 M0 four times, and these addresses also look same, right? Here we can do some optimization, that is called supernetting. That is called supernetting, or that is also called address aggregation. So basically, instead of saying that M0, 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 what I can say, I can let me give you a brief idea. What I can say, if if network ID, so it can just have one row that says, instead of these four rows, it can just have one row that says if network ID start with 140, right? If that start with 140.x.x.x, then the interface should be M0. Otherwise, interface should be M1. Isn't it fair enough? If the network ID starts with 140, then it should go to M0. Otherwise, it should go to M1, because everything is starting with 140. So instead of saying like this, I can just say if the network ID starts with 140. That is one idea, but it is not very precise. Maybe if I want to be more precise, then I can say that okay, if the network ID start with maybe not just 140, maybe I can say 140.24, then x.x, right? Then go to M0. Otherwise, go to M1, because everything is having 140.24, 140.24. So I can say if the network ID start with 140.24, then go to M1. Otherwise, go to M1. But it is also not very precise. I can be, or obviously I can be more precise. I can say if the network ID is 140.24.7 dot something, then go to M0, right? Can I be more precise? I mean, by just looking at it, I'm not 100% sure if I can be more precise, but I need to look it out. I need to look more precisely. So this process is called address aggregation or supernetting, in which what we are doing, we are trying to aggregate some networks, we are trying to just optimize the routing table. How? We are just going to say that instead of having 4 entries, I can just have one entry which is saying that if the network ID start with 140, or maybe more precisely 140.24, or even more precisely 140.24.7, and even maybe I can have very like more precise optimization, so I can be more precise, but by just looking at it I'm not sure. So the formal procedure of doing it is called address aggregation or supernetting. Let's see what it does. So address aggregation basically does what? It combines networks into one of the network. So if you remember subnetting, then in subnetting what we are doing? So it is subnetting, not supernetting. Like I'm just giving you a quick recap of the subnetting. In subnetting, what we were doing? It was the network ID, it was the host ID, and then we were dividing this into different subnets. So we were just saying that here for each subnet, like I was borrowing some of the bits from the host ID. So this is subnet number, right? And this is host ID and this is network ID. So after division, there will be extra field that will represent my subnet number. Now initially let's suppose this was 24, which means 24 bits are fixed. Now for each subnet, the subnet number is also fixed, right? So it will be, let's suppose 2 bits are subnet number, then it will be 26, which means I'm borrowing some of the bits from the host ID and then I'm merging them into network ID. So this prefix length is getting increased here from 24 to 26. But here the prefix length will get decreased, which means from 24 it will get decreased to something. Let's see how. So what is my idea? Idea is that I want to merge all of this logically, which means just for the routing table. How we are going to do it? Just look at this. What we are going to do? That's very simple. Step 1, write addresses in binary. Step 2, see what is similar or common. Step 3, just merge them. So let's see how we are going to do it. Let me copy this in the next page and then I will tell you how we are going to merge these networks. So suppose I want to merge these 4 networks. So what does step 1 says? It says that write everything in binary. So I'm not going to write everything actually, because here this 192 and 168 is common to everything, so I'm not going to write it in binary. I'm just going to write it which are not common. I mean decimal, at least it is not common. So I'm going to write everything in binary. So it is basically 0, which will be 0, 0, 0, 0, 0, 0, 0, 0, and then dot something like dot 0, right, decimal, and then 192.168.1, which is 0, 0, 0, 0, 0, 0, 0, 0, 1 dot something, right, which is 0, and then 192.168 dot 0, 0, 0, 0, 0, 0, 1 0 dot 0, and then 192.168.0, 0, 0, 0, 0, 0, 0, 0, 1 1, right? This is what these 4 networks are. This first network is saying that initial 24 bits are fixed, right? Initial 24 bits are fixed. This second network is saying initial 24 bits are fixed. But if you look at carefully, then if you want to merge these 4 networks, then can you say that initial 22 bits are fixed? Initial 22 bits are fixed, which means can you just say that these 4 networks combinedly be 192.168 dot this like if you put this in a decimal, these bits along with 0, 0, so it will be just 0.0, and then can you just say 22? What does this mean? It says that initial 22 bits are fixed, which are zeros, and later bits are changeable, which is okay, right? I mean, this combinedly, this network, these 4 networks can be combined into this just one network, which says that initial 22 bits are fixed, and then you can change the bits. See, each individual network is saying initial 24 bits are fixed, and then you can change the bits. So anyway, these bits are changeable. Everyone is agreeing that these bits are changeable. But Supernetting is also agreeing that these bits are also changeable. These bits are also changeable. This is what it is saying. So it says that anything that start with 192.168 dot these zeros, then these are just one of this network basically. See what is common in all of this. 192 is common, 168 is common, and these bits are also common. So what I'm going to say, that anything that is starting with 192 to 168 dot these bits, this is what I'm saying, right? So 192 to 168 dot these bits, anything which is starting with this, then it is belonging to one of this network, right? I hope you got the idea. So what was my aim? My aim was that I want to summarize these information into just one information, that I want to say that, see, anything that start with 192, then it should belong to one of this network. More precisely, anything that start with 192 to 168, then it should belong to one of this network. Maybe 192 dot 168 dot in binary, like if I talk in binary, then dot 6 zeros, then this is one of this host is one of in this network, right? So this is how I can aggregate these four networks. Let's take one more example and let's try to understand this more clearly. Suppose that you have one network which is like this: 192.128.0.0/9, and there is one more network which is 192.0.0.0/9, and you want to merge these two networks. So what to do? For that, first step is that you need to first write this in binary, which means I'm not going to write 192 because 192 is anyway common, so I'm just writing 128 and 0. So 128 means 1 followed by 7 zeros, so there will be 7 zeros, and then dot 0 dot 0. And for another address you can write in similar way, which is 192.0.0.0.0.0.0, right? Now that's very simple. Now what you need to do, you just need to identify that till what point things are common. So just check till what point things are common. Till only this point things are common, which means you can say that you can merge them in this way: 192.0.0.0 in this way, slash only 8 bits are common, so slash 8, because these 8 bits are fixed. So these two networks got merged into this one network like this. Suppose that there is one more network which is 192.192.0.0/10, and they ask you to merge these three networks. Then let's just see how we are going to do. We are first going to write in binary, like for first network this is the binary representation, second this is the binary. Like this is not completely binary, but whenever it is required I'm writing in binary. And for 192 it is 128 plus 64, which is 192. Then it will be 1 1 followed by zeros, 0 0 0 0 dot 0 dot 0. So this is slash 10. Anyway, now just check till what point things are common. Things are common till this point only. So these three networks will also get combined into just this network only, right? Which is 192.0.0/8.0/8. I hope you got the idea. Now let's look at this configuration. Here I have one router, that is R1, which is connected to these four organizations, and there is one router that is R2, which is connected to like a router R1 and some outside world. This example like we have just seen. Now here I want to have a routing table for R2. So in case of R2, I want to have something like this. I want to have just one entry which tells me that something that starts with 140, then I will send it to M0. Otherwise, I will send it to, this is default route, I will send it to M1. Some sort of these kind of entries I want to have in router R2 forwarding table, right? Which means this router, with respect to this router, it does not matter whether there are four organizations. Only thing matters, like things are starting from 140. So it's just like that if you are in India and if you want to send something to US, or maybe you are in US, you want to send something to UK, then it does not matter whether it is going to France or London, right? Since you are in US, it does not matter for you. You will first send it to UK. Now UK will distribute it, right, to France or London. So similarly, for with respect to R2, it does not matter which organization it is, as long as it just sees that something that is starting with 140, so it will just send it to M not root. So that sort of thing I want to have for R2. For that, what I need to do, I can just merge these four networks into one network. Let me just merge these networks. One of the network is 140.24.7.0.7.0/26. Another network is 140.24.7.64/26, and then 140.24.7.128/26, and then 140.24.7.192/26. These are the four networks, and that these networks I want to merge. Now let me write that in binary. So I'm not going to write 140 and 24 because anyway .7, because anyway these are common. So I just want to check what are the things common after it, because these are anyway common. And then this is common. So okay, let me just write it 140.24.7, 140.24.7, then 140.24.7, then 140.24.7. And now you have 64, which means 0 1 0 0 0 0 0 0, and here you have 128, which means this. Then you have 192, which means 128 plus 64, which means this. And now just check what are the things that are common. Till what point things are common? Till this point things are common. So you will just say that you are going to merge them into one of the network, which looks like this slash, this is 24 bits which are fixed, so slash 24. So these four networks got merged into slash 24. I mean this slash 24, right? This is how we are merging these four networks. Now suppose like there is something like this, there is some networks like this, which is 140.24.7.0 slash maybe 26, and then 140.24.64.0 slash 26, 140.24.128.0 slash 26, and then 140.24.192.0 slash 26. See here what I did, I have taken this .7.0 instead of 0.7. Sorry, instead of 7.0 and 7.64, I have taken here, I'm just changing this 7, 64, 128 and 192. So I'm changing this third octet instead of making it fixed. Now just check how we are going to convert this into one network. We are going to write into binary first, which means 140.24, it is common, and then 7, which means 0 0 0 0 0 1 1 1, and then .0. Then it will be 140.24.64 means 0 1 0 0 0 0 0 0 .0. It will be 140.24.128 means this, and then 192 means this. Then just check till what point things are common. Things are common till this point only, right? So it will be 140.24.0.0/16. This will be aggregation of these four networks. Now you may say that this is a huge network because there are too many hosts here. There are like 2 power 16 hosts here, and here we like, if you combine these networks, like in one of the network it is 2 power 5 or 2 power 6 hosts, and these are the four networks. So only 2 power 8 hosts are there in these networks, and this network is having 2 power 16 hosts, which is like, which is I mean not just twice, it is 2 power 8 times of this, right? Which is like very huge network. So this network is very huge, and this network is, these four networks combinedly are small networks. So how can you have huge network out of these small networks? Like, your question is valid, and the answer of this question is that we are not actually merging it. I mean, we are not saying that we have merged it. It is just with respect to this router. For this router, if something is starting from 140.24, then this router will send, with respect to this router will send packets to packets in this direction, right? This is with respect to this router only. See, this network is a huge network, that I agree, but with respect to this router, if let's suppose there are two options, like something is starting from 150 dot something and something is 160 dot something, then I can just say that if something is starting from 140.24, then you send packets in this direction. That's what I'm saying only, right? I hope you got the idea. Now let's move to the next slide. So basically we have this as a routing table for R2, which means these four networks are getting combined into this network. See here, this is 140.24.7.0/24. So these four networks got combined into this network, and now with respect to R2, like I just have this as one network, not these four networks. This is very easy. Now, there may be a scenario where your organization may not be physically together, which means one of the organization may be far from another organization. So, see in this diagram, see these three organizations are here, but this organization 4 is here, and these organizations are not physically close to each other. So, in this case, what to do? I mean, if you make the routing table for R2, then how it should look like? So with respect to R2, you can still combine these three networks, and then you can just say that these three networks are just one network. If you're going to combine, then it will be like the previous result only. But let me quickly show you. This is 0000, and then 140.24.7.64 means 101000000, and then 140.24.7.128 means this. Now if you combine these three networks only, see these are like, if you combine four networks, then also like earlier there were four networks. See 140 dot like we have combined these four networks, like organization 4 were here, so we have combined these networks. Earlier we have combined these networks. Now we are combining only these three networks, we are not combining this. See earlier we got this as a result, now also we are getting this as a result, because just look at these three. Till what point things are common? Till this point only things are common. So these three networks will also get the same supernet, which means this dot 0/24. Earlier also we got the same. So with respect to R2, this is still like this. These three networks are forming this supernet. So for R2, if I write the routing table for R2, it will be having one entry like this: 24.7.0/24, then m0. And if it is, this is important. See here, 140.24.7.192/26/26, then it should be m1. Otherwise, default it should be m2. This should be the routing table for R2 now, right? I hope you got the idea. This should be the routing table for R2. See, this is because of these three networks. This entry is because of this network, this organization, and default is because of this M2. Now here is one trouble, and here is one problem, and we have solution also. But let me pose a question first. Suppose there is some packet that is coming to R2. So we have this is routing table for R1, and this is routing table for R2. So we have routing table for R2. R1 routing table is very easy. I mean, for R1 these are the three different networks. For R1 you can't supernet, but for R2 you can supernet. Now this is actually, this is fine, but let me ask you a question, and then you need to tell me the answer. So the question is that suppose some packet at R2 is coming that actually belongs to this network. So let me take one of the host here, maybe 140.24.7.193, which actually belongs to this organization, and with this destination IP it is coming to R2. Now my question is that how R2 is going to forward this packet. Ideally it should get forwarded to M1, but is R2 doing this job? Is R2 forwarding this packet to M1 or not? Let's just check it. How we are going to check it? See, what we need to do, we will take this and we will apply this mask, 26 masks, and then we will check whether this belongs to this network or not. If you apply 26 marks to this IP address, then you will find out that network ID will be 140.24.7.192. How we are going to apply? See, we have this as destination IP. This is destination IP, which is 140.24.7.193, and we need to apply the mask of 26, and then let's just check what I'm getting as a network ID. So if I apply mask of 26, which means initial 26 bits are fixed, then everything is 0 for the network ID. So if you do that, it will be 140.24.7.192. Why? Because 193 is just 1100 and then 0001. This is 192 plus 1. and 192 itself is 128 plus 64, 128 plus 64 plus 1. This is how we are getting 193. Now if you apply this, then you are going to get this as a network ID, and since this network ID is matching with this network ID, so it should ideally forward to this organization or this interface, right? So my packet should get forwarded to M1, but there is a catch. Catch is that if you apply this mask also to this destination IP, which means if you apply, so this is one of the scenario. If we apply mask of, this is destination IP, if we apply mask of 24, then let's just see what is going to happen. 140.24.7.193. If we apply this mask of 24, then what we are going to have, you are in fact going to have like 140.24.7.0, because 24 bits are this and everything is 0 for the network ID. So you are going to have this. Is this matching with my network ID? Yes, this is also matching with my network ID. You see a problem? So two things are matching with my network ID. This is also matching, this is also matching. Now in this case, what to do if two entries are matching? This is my question. First of all, why it is happening? This is happening because this supernet, out of these three networks we have made one supernet. This supernet is actually not just having these three organization addresses, it is basically superset of this, which means it was actually having organization 4 addresses also. I mean, this was having too much addresses, right? That is why, like, this is some broader set. Basically this is some broader set. That is why it is matching basically with two entries. So in this case, there is a rule that is called longest prefix match. Longest prefix match. This says that forward the packet to the interface which is having longest prefix. Forward to the longest prefix interface. If there are multiple match, if there are multiple matches. So here, since there are multiple matches, it will forward to M1. It will get forwarded to M1. Why? Because this 26 is greater than 24. That is why it will get forwarded to M1. And that's how we are doing supernetting also, and we are avoiding the confusion. See, this 26 is more precise and 24 is basically some broader set, and 26 is more precise. That is why we are basically applying the longest perfect match rule. And this rule says that if there is a confusion, then always forward to longest prefix interface if there are multiple matches, right? That is why this packet will get forwarded to M1 only. I hope you got it. Now let's take one more example. Suppose like you are in US and you want to forward some packet to UK, and there are like 3 universities to which this router is connected to, Cambridge, Oxford or Edinburgh University, and these are having some different IPs. But as per Newark router, it does not matter. Like if something is starting from 192.2.24, I'm just speaking roughly. If something is starting from 192.24, then it should get forwarded to this direction. For US, it only matters like whether you are going UK or you are going to some other country, right? For US, it only matters. It does not matter that in UK where you are going, where this packet is going. So what should I write in the forwarding table of Newark router? What I need to do? Very simple. I need to just merge these 3 networks. So let's just do it. How we are going to do it? We are just going to write this in binary, which is 192.24. Instead of 0, let me write in binary dot 0, and then 192.24.16 means 0001, and then 0000.0, and 8 means 192.24.0000, and then 1000, right? So these are the 3 networks. Just check till what point things are common. So things are common till this point. Things are common till this point, which means this will get combined into 192.24 dot, like this is already 0, and for network ID these will be 0. So it will be .0.0 slash, what should I write here? See here, 8 and 8 16 plus 3 19. So I should write 19. So basically for this router, the aggregated or the supernet will be 192.24.0.0/19. So in the routing table of the New York router, it should be like this. That let's suppose this interface is M node. So if some packet is coming for this network for this network, then it should get forwarded to M node. This is the routing table for New York, right? So you are forwarding from New York to UK. See here, we only have one aggregated prefix, which is 192.24.0.0/19. And here we have three different IP addresses, three different network. So once it comes to this router has to obviously have these three entries. So it will distinguish like to which university we are going. This packet is going. That's how supernetting works. I hope you got the idea.